My topic is cooling of a hot metal ball in air. A spherical metal ball of radius r is heated in an oven to a temperature of 600 degree Fahrenheit throughout and is then taken out of the oven and allowed to cool in ambient air at 75 degree Fahrenheit by convection and radiation. The thermal conductivity of the ball material is known to vary linearly with the temperature. Assuming the ball is cooled uniformly from the entire outer surface, obtain the differential equation. The solution will be like this. The ball is initially at a uniform temperature and is cooled uniformly from the entire outer surface. Also, the temperature at any point in the ball will change with time during cooling. Therefore, this is a one-dimensional transient heat conduction problem, since the temperature within the ball will change with the radial distance or and the time t. The thermal conductivity is given to be variable and there is no heat generation in the ball. Therefore, the differential equation that governs the variation of temperature in the ball in this case is obtained from equation by setting the heat generation term equal to 0. We obtain 1 by r square into dou by dou r to r square k dou t by dou r equal to rho c into dou t by dou t, which is one-dimensional transient heat conduction equation in spherical coordinates. And then another problem it involves in a heat conduction in a short cylinder. A short cylindrical metal billet of radius r and height h is heated in an oven to a temperature of 600 degree Fahrenheit throughout and is then taken out of the oven and allowed to cool an ambient air at 65 degree Fahrenheit by convection and radiation. Assuming the billet is cooled uniformly from all outer surfaces and the variation of the thermal conductivity, the solution for this problem may be the billet is initially at a uniform temperature and is cooled uniformly from the top and bottom surfaces in the z direction as well as the lateral surface in the radial r direction. Also, the temperature at any point in the ball will change with time during cooling. Therefore, this is a two-dimensional transient heat conduction problem, since the temperature within the billet will change with the radial and axial distances r and z and with the time t. That is t equal to t of r z comma t. The thermal conductivity is given to be constant and there is no heat generation in the billet. Therefore, the differential equation that governs the variation of temperature in the billet in the case of obtained by setting the heat generation term and the derivation with respect to the equation. The boundary and initial condition will be like this. The heat conductions above were developed using the energy balance on a differential element inside the medium and they remain the same regardless of the thermal conditions on the surfaces of the medium. That is, the differential equations do not incorporate any information related to the conditions on the surfaces such as the surface temperature or a specified heat flux. Yet we know that the heat flux and the temperature distribution in a medium depend on the conditions at the surfaces and the description of a heat transfer problem in a medium is not complete without a full description of the thermal conditions at the bounding surfaces of the medium. The mathematical expressions of the thermal conditions at the boundaries are called the boundary condition. From a mathematical point of view, solving a differential equation is essentially a process of removing derivatives or an integration process, and thus the solution of a differential equation typically involves arbitrary constant. It follows that to obtain a unique solution to the problem, we need to specify more than just the governing differential equation. We need to specify some conditions such as so that the forcing the solution